This is Global Circulation, Unit 12. We are going to build on our Unit 11 principles of the governing forces in the atmosphere, the pressure gradient force, the Coriolis force, and friction. We are now going to take a little bit of a broader perspective and look at both hemispheres about the circulation patterns that we see. You're looking actually directly down on the North Pole in this particular satellite image animation. And if you kind of pick out some patterns here, you can see the propagation of these systems in the mid-latitudes is generally from a west to east fashion. In the tropical regions, we actually see an east to west movement of the clouds and the thunderstorm activity. And you can't see down on the polar regions because of the blocking of the satellite, but you would also see there we have an east to west flow just like we see in the tropical regions. So we have this east to west, west to east, and east to west circulation of the cloud patterns that are being picked up by this particular water vapor image. You can vividly see some of these counterclockwise and clockwise circulations. For example, in the Atlantic Ocean, we have a very broad clockwise circulation, or an anticyclone. This would be associated with an area of high pressure. We have some strong cyclonic or counterclockwise activity here in the northern hemisphere. So here's our big storm systems, our cyclones. Here's another one out in the Pacific, and these are just general circulations of counterclockwise movement in the northern hemisphere. And again, we had these names in Unit 11 of cyclones and anticyclones. So please review the Unit 11 lecture if you're having difficulty picking out which is a cyclone and which is an anticyclone. So this is observation. We observe these kind of three belts of wind, and we want to talk a little bit about the theory that governs why these circulation patterns occur in the atmosphere. So why do we see this general westerly movement in the mid-latitudes, and why do we see this general easterly movement in the tropical regions? You know there's easterly movement in the tropical regions because we have hurricanes that form all over the coast way out here in very far western portions of Africa. They traverse in an easterly fashion across the Atlantic Ocean, then they can influence places like the Gulf of Mexico or the east coast of the United States. So we know that hurricanes come from the east to the west, but in Chicago we know that most of our weather comes from the west and actually goes to the east. So what are the general ideas of the guidelines that are forcing these sort of atmospheric patterns? We're going to get into that today in Unit 12. Okay, so we're going to talk about the general circulation of the atmosphere. The first thing that we're going to do are make some assumptions about make this whole system a little bit more simplistic. We know that the Earth is a very complex system, so we're going to start with some very basic and silly assumptions. We're going to take those assumptions away one by one and see if we can get really, really close to what we actually observe. Okay, so the first assumption that we're going to make is that the Earth is uniformly covered with water. There's no land. If we have no land, then we know there is no difference in heating between the land and the water, because we know water has a much higher specific heat than land. Water takes a much longer time to heat up and cool down, so we would have these temperature differences that we don't really want to deal with. We're going to take away all the land, and we're just going to assume that everything's water. The second thing that we're going to do is focus the solar activity directly over the equator, so we're not going to tilt the Earth on its axis, essentially. Solar declination is going to always be at the equatorial region, and therefore we always have this intense heating going on right at the equator. We know that's not the case. We know the Earth is tilted on its axis, and we know that solar declination ranges between the Tropic of Cancer and the Tropic of Capricorn. So what we're essentially going to do here is make the Earth's tilt 0, and we're going to cover the entire Earth with water, so take away all the land, and we're also not going to allow the Earth to rotate. So we're not going to have days. We're just going to have one side of the planet that's always light and one side of the planet that's always dark. Now that sounds like a really silly assumption. When we do that though, what kind of circulation pattern do we get? We get something in the Weather Studies Manual called the single cell model. The single cell model is very easy to depict. We're just focusing here kind of on one side of the globe. What we do is get this intense heating going on at the equatorial regions because solar declination is not changing. We don't rotate the Earth, so we don't have to deal with the Coriolis force. And what you get is this one giant convective cell, almost like a lava lamp, where the Earth is intensely heated by the incoming solar radiation. That air becomes less dense, it rises near the equator, and we get this very large convective cell. Okay, cold air sinking at the north and south poles, returning to the equatorial regions to be heated, and then kind of sent back to the polar region. So it's a very large example of a lava lamp. And what you would always get in this particular example, if you were in the northern hemisphere, is a northerly blowing wind at the surface. So if you were in Chicago, wind would always be out of the north. All right? If we take the single cell model and we keep the idea of the land, so we keep the idea of let's have water only. And I know this example has land behind it, but let's just assume that there's only water. Let's keep the example that we have solar declination always at the equator, so we're not going to tilt the Earth just quite yet. But what we will do is allow the Earth to rotate. So here we were not allowing the Earth to rotate. Let's take the single cell model, allow the single cell model to rotate, and what you get because of the rotation is the 3-cell model. The rotation of the Earth allows, essentially breaks down the single cell into 3 cells. And this is seen on other planets as well. Jupiter is a very fastly rotating planet, and it has many more cells than the Earth does. In fact, it has almost 6 cells that we can identify because of the fast rotation of the planet of Jupiter. If the Earth rotated slower, we would not have 3 cells. We might have more like 2. It all depends. You will break down this cellular activity due to the rotation of the Earth. This is very easily seen by water in tank experiments. If you have a tank of water and put it on a rotating platform, drop in some food coloring, rotate it faster or slower, you'll see that the eddies will break down into different cells depending on how fast the rotation is. So, because we rotate about once every 24 hours, that equivalates to about 3 of these cells. Okay, and there's some mathematics that you can do to kind of figure that out, but we're not going to worry about that. What I really want to do now is focus in on the cells and sort of why we have the cells and what they essentially force the weather patterns to do. And we'll kind of focus for the first part on the northern hemisphere. Because of the initial assumption that the Earth is not tilted, so we have all the incoming solar energy coming in at the equator, the tropics still receive a lot more heat. Okay, so a lot more energy is still coming in in the equatorial regions. We still have kind of a deficit going on at the poles. Because of the rotation, we break down the first cell from about the equator to 30 degrees north. So we have a cell from the equator to 30 south and a cell from the equator to 30 north. This is known as the Hadley cell. The next cell is from 30 north to 60 north. That is known as the Ferrel cell. And we also have a cell from 60 north to 90 north. That is the polar cell. So we have the Hadley, the Ferrel, and the polar cell. We have a Hadley, Ferrel, and polar cell in each hemisphere. So there are 6 cells total, 3 cells in each hemisphere, and each hemisphere has a Hadley cell, a Ferrel cell, and a polar cell. You can see what the Hadley cell looks like. It has rising air at the equator, sinking air at about 30 north. Also with that sinking air, it has rising air at about 60 north. And again, sinking air at 90 north. So we're going to kind of take a look at all of these models, these 3-cell models. We're going to put them all together. We'll talk about each of the cells in particular here individually. And then we'll put our entire perspective together to see why the winds blow the way they do in different portions of the latitude bands. Okay. So this is the full depiction of the 3-cell model. You can see your Hadley cells here. We have the Ferrel cells between 30 north, 60 north, and 30 south and 60 south. We also have the polar cells from 60 north to 90 north and 60 south to 90 south. So what ends up happening, because we have intense heating at the equatorial regions, the air is rising. We know where we have rising air, we have low pressure. Okay, and you can see we have rising air here, sinking air. Whenever we have sinking air, we're going to find areas of high pressure. That's the general rule of thumb, right? If the air is rising, it's low pressure. If it's sinking, it's high pressure. So where we have these downward moving portions of the eddies, that's where we're going to see high pressure. Where we have the upward rising air, that's where we see low pressure. So near the equator, we have something called the ITCZ, the Intertropical Convergence Zone. That's where the air is essentially converging and rising, and we find a lot of thunderstorm activity near the ITCZ. Now you might be asking yourself, why is the wind blowing in from the northeast in the northern hemisphere, but it's blowing from the southeast in the southern hemisphere? Well, let's take let's think about our forces that are kind of governing this. We are allowing the Earth to rotate now, so we have to think of the Coriolis force. Imagine yourself standing on the high pressure, standing on this subtropical high pressure in the northern hemisphere, and pointing towards the equator. Air would accelerate from high to low, from the pressure gradient force. It would then be deflected to the right of motion. So again, stand on the high, face towards the low. As we begin to move towards the low pressure system, we are deflected to the right. So that's not to the left, right? Because we're facing towards, stand on the high, face towards the low, and then go to the right. So that results in sort of an easterly wind direction. In the southern hemisphere, we stand on the high, point towards the low, and we go to the left of motion. So we achieve a southeast, sort of east wind in the southern hemisphere. We also get an east or northeast wind in the northern hemisphere. Okay? These are called the trade wind easterlies. We'll talk a little bit more about those in just a minute. In the mid-latitudes in the northern hemisphere, stand on the high, point towards the low, go to the right. We come up with westerly winds in the mid-latitudes of the northern hemisphere. In the southern hemisphere, stand on the high, point towards the low, go to the left. We also achieve westerly winds in the mid-latitudes. In the polar regions, we stand on the high, point towards the low, go to the right, so we achieve an easterly wind again. And in the southern hemisphere, we stand on the high, point towards the low, go to the left, so we also achieve easterly winds. So it's because of this general circulation, these Hadley cell breakdowns of high and low pressure, that we get different bands of winds, westerly versus easterly, in different latitude belts on Earth's surface. So in Chicago, we're in the mid-latitudes, we get these westerly winds. Tropical regions, so when we experience tropical cyclone activity across the Atlantic, it generally propagates across the Atlantic in an easterly fashion, going from the east to the west. All right. The different cells are separated by three sort of features. The Hadley cells are separated by the ITCZ, this area of rising air. So we have easterly winds converging at the equator. That air rises. We have lots of persistent cloudiness, lots of rainfall. A lot of your rainforests will be found in the ITCZ regions. That's area of rising air. Where the air is sinking and diverging away, we find some of the world's largest deserts, like the Saharan Desert, where we have subtropical high pressure. The air is sinking and diverging away at the surface, so you're not going to have very many clouds or precipitation. So the Hadley and Ferrel cells are separated by areas of subtropical high pressure, or subtropical anticyclones, if you want to call them that, that's fine. And then finally, the Ferrel and polar cells are separated at about 60 degrees north and 60 degrees south by what we call the subpolar front, or what we're going to term in a little bit here, jet streams, or winds of very fast speed that kind of mark the difference between very warm and very cold air. Let's focus on each of the cells so we can get a little bit better idea of exactly what we're talking about. The first here is the Hadley cell. We said it is right at the equator, between the equator and 30 north and between the equator and 30 south. So we have two Hadley cells, one in each hemisphere. Very strong heating at the equator causes the air to rise and diverge outward away from the equator towards the poles. Okay? So we heat the air and it creates a convective cell in the northern hemisphere and a convective cell in the southern hemisphere. That sinking air near 30 north and 30 south begins to come back to the equator to be heated up. As it comes back to be heated up, it is influenced by the Coriolis force. In the southern hemisphere, it deflects it to the left. In the northern hemisphere, it deflects it to the right. We end up with an easterly direction in both of the hemispheres. The Hadley cell is a thermally direct circulation, meaning it's being driven by these differences in incoming solar energy. So the solar energy is kind of forcing this. It's very similar to a lava lamp or a convective cell. The ITCZ will sort of shift north and south, so the Hadley cell will shift north and south with solar declination, so it won't always stay put right at the equator. It might migrate a few degrees north or south of the equator as the solar declination begins to switch through the seasons. And because of the Hadley cell, because of this air returning to the surface, at 30 north and 30 south, and then kind of coming towards the equator, we get easterly winds in both hemispheres in the tropical regions. We call these the trade winds. Okay, if you like to drink trade wind iced tea, this is where the name came from. These are easterly surface winds in the tropical regions between 30 north and 30 south. Okay, so that air is kind of traveling in an easterly fashion. It converges together near the ITCZ, which is about located near the equator. That air converges. It can't go into the water or the ground. It must rise. It rises and forms clouds and precipitation and thunderstorms. And we have a lot of precipitation found near the ITCZ. Okay. Where the air, right underneath where this air is sort of rising, all right, there is no wind. So you can imagine, right underneath this cell, so we have wind here and wind here, but right underneath where the air is rising, we really have no wind. The air is going straight up. The pressure gradient is very weak. We know when the pressure gradient is weak, we don't have fast wind speeds. So the winds are very light, and we call this area of the globe the doldrums. So very close to the ITCZ, we say the doldrums. You may have read this in literature before, being down in the doldrums. I always like to think of Central America as being in the doldrums. It's very monotonous weather. Every day you kind of have thunderstorm activity, but there's really no strong storms. It's just every day you can sort of set your watch at about 3 o'clock to thunderstorm activity. The thunderstorms come, they go, and the weather is very similar day after day after day after day. There are also another nickname. If you go a little bit further north and a little bit further south to about 30 north and 30 south, right underneath the subtropical areas of high pressure, we have the horse latitudes. The horse latitudes are 30 north and 30 south. The air is sinking right above your head, and because the air is sinking right above your head, there is also very light winds. So if you take back a look to this idea of the three-cell model, we have very light winds right underneath all of these features. So between the features, we have strong winds, and you can see the relative strength of the winds are shown by the vectors. So the mid-latitude westerlies are always the strongest, the trade wind easterlies being the weakest. But right underneath the features, we kind of have no wind because the air is either probably rising or sinking above your head. In this case, the air is sinking above your head at 30 north and 30 south, and we have very light winds. The folks that were doing a lot of trading across the Atlantic, sailors, they had very big issues crossing 30 north and 30 south latitude because of the very light wind, and oftentimes they were trading spices or livestock, and one of the biggest things they were bringing over to the Americas were horses, and oftentimes they would throw the horses overboard to lighten their load, a very cruel practice, but they needed to be able to move. Their ship was a little bit too heavy, and without very strong winds they weren't able to move. And so you can see with the global circulation, if you wanted to sail to the Americas, you would do so in the easterly trade winds. If you wanted to sail back to Europe, you would do so in the mid-latitude westerlies. The problem is if you get right underneath this area where there's subtropical high pressure, there's really no wind, and the only way to go anywhere is to lighten your load big time, and so they threw the horses overboard and they got the name the horse latitudes. The next cell, the cell between 30 north, 60 north, 30 south, 60 south, is the Ferrel cell. This circulates air between the subtropical areas and the subpolar lows, so the jet stream at 60 north and 60 south. The Ferrel cell is an indirect circulation caused by the the motion of the adjacent cells. So you can imagine yourself, if you ever played with gears or connect sets as a little kid, if you have a gear that's rotating this way and a gear that's rotating this way, the gear in the middle has to rotate the opposite, right? So if you have a gear that's moving here and you just put a gear in here, it will automatically rotate the other way, and therefore the circulation of the Ferrel cells in both hemispheres is a result of the direct thermally circulated Hadley cells. So these are what we call indirect circulations. They're basically a circulation that is a byproduct of the fact that we have a direct circulation next to it. The Hadley cell is direct. It's thermally direct. It's driven by the intense heating near the equator. So that air rises, then it sinks at 30 north, 30 south because of the rotation of the Earth. And due to that sinking motion, we create another cell here at 30 north to 60 north and 30 south to 60 south, which we call the Ferrel cells. Okay? So, This creates westerly winds in the mid-latitudes, again, because if we have sinking air and then it's returning, so go high to low pressure, high to low, go to the right, Coriolis force says, that creates a westerly wind in both hemispheres, high to low, go to the left, and we create this general wind flow of a westerly fashion in the mid-latitudes. So if you ever asked yourself, I'd like to know exactly why weather moves west to east for us here in the Chicago region, it is due to the circulation of the ferrule cell at the surface. Wind is basically blowing from south to north. It is deflected to the right due to the Coriolis force, and we get a westerly wind. Okay. We're going to talk a little bit more about predominant flow in the United States here in a little bit, but this should at least answer your question of that very first satellite image of the circulations that we were looking at and kind of why weather was moving from west to east in the mid-latitudes. The final cell is the polar cell. The polar cell is also a thermally direct circulation, and it's thermally direct because it's really not getting any sort of solar incoming solar radiation, and so the air is very, very dense. It sinks. It's very cold and dense, and sinks at the north and south poles due to the high pressure. Air is sinking. It's high pressure. It's very dense. It returns to the latitude bands of 60 north and 60 south. As it returns, it is deflected to the Coriolis force. So we have this high to low, go to the right. That is an easterly wind. High to low, go to the left. It's also an easterly wind in the southern hemisphere. So, without a tilted Earth, without land, this is what the flow at the surface would look like if you were to draw your three-cell model. So we'd have easterly winds in the trade regions, subtropical areas. We have westerly flow in the mid-latitudes and easterly flow in the polar regions. Looks pretty good. Second bullet point. It explains surface winds very well. Okay. Here's the actual. So here's our assumption. Here's our three-cell model with the assumptions made. If we throw in the land and tilt the Earth, this is on average what we get. So you can see polar easterlies come a little bit further south, but in general, our theory, our circulation with the assumptions, looks a lot like what we see in observations. Okay, it's very close at the surface. However, it does not explain the upper level winds as well. Okay. So if you're explaining the winds at the surface of the Earth, the three-cell model would do a great job. The three-cell model does not do a great job when you take a look at winds in the upper levels. In fact, we're going to see here in a bit, the winds in the upper levels are almost always westerly. And we'll take a look at why here in just a second. I'm going to skip those two slides. I want to show this. Well, hopefully I can get this to work here. Doesn't look like this animation is going to work, but essentially what I would do here is I'd click play, and as it goes through the course of the year, the ITCZ would shift north and south, the Hadley cells would shift north and south, the areas of precipitation would shift north and south with the ITCZ. So it's just kind of showing you where the general areas of high and low pressure are, or cyclones and anticyclones, shows you the thermally direct circulation, and it just kind of migrates back and forth here a few degrees latitude as solar declination changes. So not a big deal, it was just a little bit of an animation there to help you visualize what was going on. As the ITCZ shifts, it brings a lot of much needed rainfall to portions of the globe that would otherwise not experience a lot of rainfall. And a great example of this is in North Africa, taking a look at the Saharan Desert and an area called the Sahel, which is a transition zone between the Central Africa rainforests and the desert region. So Africa is a pretty amazing country. You can go from rainforest to one of the driest places on the Earth's surface. And in between those areas, we have this very large gradient in rainfall. You can see anywhere from 2 feet of rainfall in southern portions of Chad in Sudan. You go to the northern portions of Chad and you're talking less than an inch of precipitation every year. So the country of Chad is a pretty amazing place. You have the Sahel, you have the Central American rainforest, which gets over 2 feet of rainfall every year, and then you go north of that and you get something like 1 to 2 inches. In the central portion of the country, we have a transition zone. That transition is the Sahel. And all of this gradient is created, this very large change in rainfall is created by the shifting ITCZ. So as the ITCZ moves north, it brings all this much needed rainfall, and then it shifts back south. And so you're kind of on the fringe here in some of these areas. The ITCZ does not shift north into places like Egypt, Libya, and Algeria, even Tunisia, where these places are very, very dry. They're under the influence of the subtropical anticyclone, sinking air, no clouds, no precipitation. All right, and so the most sensitive areas are these transition zones, places like Chad. And you can imagine, let's say you're in central Chad, and the 1 year the ITCZ only shifts to southern Sudan. Okay, so the ITCZ only makes it here. Instead of getting your normal 8 inches of rainfall, you get nothing. And all of a sudden, you are on the fringe of becoming an expanding desert because you are very sensitive to the amount of rainfall you get every year. You rely on 8 to 4 inches every year. And if you don't get that, you turn into a desert. So the plants and animals and the biodiversity in the communities and the biomes, etc., that live in these areas are very, very sensitive to the fact that the ITCZ will indeed shift far enough north to provide them with rainfall. All right, we said our 3-cell model was not a great depiction of upper level winds. Let's talk about why. Okay, at most latitudes, except right at the equator, upper level winds are westerly. So it doesn't matter if you're at 5 degrees north or 90 degrees north. If you go off the surface of the earth, the wind is going to be from the west to the east, a westerly wind. Why is that the case? That is the case because of these idea of heights that we talked about. Okay? If we have 2 columns of air and we heat one of them, we know the area near the tropics are much warmer. That air expands. And so we have 2 pressure levels that are essentially found at different heights. The 500 millibar surface is higher in the tropical regions than it is in the polar regions. So we create a pressure gradient force in the same altitude. So if we go up to the black line, this is 500 millibars. We know if we go straight over on this black line, the pressure over here would be something less than 500 millibars. We'd go from high pressure to low pressure. So wind would accelerate from in this image from the right to the left. So we'd have a PGF directed towards A from B to A. As the wind goes from B to A, it'll be deflected to the right or into the screen. So we'd have a vector that's pointed into the screen in this case. So if this is south and this is north and we have a vector pointed into the screen, you can see that that would be a westerly wind. Okay, so it might take you a little bit of a little bit to sort of examine this. You could also draw this out on paper if you need to. Okay, so if this is south and this is north, so if you want to label this N and label this S, as the air accelerates from B to A, because we have a pressure gradient force from B to A, it is deflected to the right. Deflection to the right would be into the screen or into the page. A vector pointed into the page would be a westerly wind if this is north, right? Never eat sour watermelon. So pointing into the page would be a vector pointing to the east, and that is a westerly wind. Okay, so it might take you a little bit to visualize that, but we always have these westerly winds because the tropical areas are warmer. So we have these heights. Right? If we're in central Texas, we know that the height to the 500 millibar surface is much higher. So in Texas, you can see here we have to go 5,940 meters to get to the 500 millibar surface. In northern North Dakota, we only have to go 5,580 meters to get to the 500 millibar surface. So we have a pressure gradient force that is directed from the oranges to the blues. So you can imagine these vectors, they're pointed 90 degrees across the line. So if you had a line here, you can imagine these contour lines. Ignore the black lines for a second, just focus on the colors. We'd have a pressure gradient force that is directed from high to low across these. As we accelerate from high to low, we would be deflected to the right, and we create this white arrow. We know it'll flow parallel to these lines of height, and that is our jet stream. This is why in all levels of the atmosphere we have this westerly wind. We have high heights to low heights. We have a westerly propagation of the winds in all portions, all latitude regions, all hemispheres. So even in the southern hemisphere, you're still going to have this west to east flow in the upper levels. This is not true at the surface of the earth, okay? Only in the upper levels. A great question is, when are the upper level winds the strongest? Okay, I posed this to my intro class, and most everyone says the winds are always stronger in the wintertime. Absolutely. Okay, why are the winds stronger in the wintertime? Take a look at this animation. This is looking down on the North Pole. The scale here is the wind speed, so the hotter colors are when the winds are the fastest, the reds and the oranges. And so as we animate from July into the wintertime, you can see that during the wintertime, the wind speeds across the northern hemisphere are the strongest. These are average upper level winds from 1985 to 1993. You can see in the wintertime, indeed, the winds are the fastest. Come July and August, the northern hemisphere wind speeds are pretty slow. You're looking at a new value, something called an isotac. So now we have isotherms, which are lines of constant temperature. We have isobars, which are lines of constant pressure. And now we have isotacs, which are lines of constant wind speed. These isotacs are strongest in the winter because the thermal gradient is strongest in the winter. Okay. So in the wintertime, if you were to take Jamaica's temperature and compare it to Alaska's temperature, you're going to get a very different number. Right? It might be negative 50 degrees in Alaska in the wintertime, and in Jamaica in the summertime it'll be a nice toasty, or in the wintertime in Jamaica it'll be a nice toasty 70, 80 degrees. Go to the summertime, it's still going to be 80, maybe 90 degrees in Jamaica, but you go to Alaska now and the temperature has shot up to 60, maybe 70 degrees Fahrenheit, and all of a sudden the change in temperature, or the gradient, between Alaska and somewhere like Jamaica is much greater in the winter than it is in the summer. When we have a very strong temperature gradient, we have very strong wind speeds. Okay, so remember the definition for a gradient. A temperature gradient is defined as the change in temperature over distance. When the temperature gradient is very large, we have very fast wind speeds. That temperature gradient is the largest in the northern hemisphere winter. Okay, so when we have winter time in the northern hemisphere, which is basically December, January, February, March, those are when our upper level winds are going to be the strongest. You always kind of experience this in the summertime. The winds are never that strong. You get into fall and spring and winter, the winds are always much stronger. The first scientist to really denote this polar jet stream and this westerly flow that broke up into these large wiggles was Carl Gustav Rossby. He was the only meteorologist ever to make the cover of Time magazine. He's a fantastically brilliant person who kind of put a name with what he was starting to see in observations. He named these waves after himself, what we can now call Rossby waves, which are large-scale wiggles in the upper level height and pressure fields. These waves exert an important impact on our day-to-day weather conditions. So if you're experiencing zonal flow versus meridional flow we said was very stormy. Zonal flow was more progressive and faster moving. But depending on which side of the Rossby wave you're on, it really dictates what kind of sensible weather conditions you're going to see at the surface of the Earth. These Rossby waves transport warm and cold air. You can imagine if you're in a pattern like this, you'll be transporting warm air where the winds are blowing southerly. You'll be transporting cold air where the winds are blowing northerly. So these Rossby patterns can really affect your day-to-day weather conditions. So we're going to go back to our jet stream. We're going to animate this now. We know that the winds, and again, you can sort of ignore the black lines for now, just focus on the colors, and you can see we have these waves, we have these cutoff areas, these circular patterns, we have almost these ridge trough sort of patterns that are happening. These are the Rossby waves that we're seeing, these large-scale undulations or wiggles in the jet stream, and they cause different surface patterns. So you can see the one just go through here. Now focus on the black lines. So there's a strong storm system. There's low pressure systems that are forming. You can see this one forming right here. It's forming near and close to an upper level Rossby wave where we just so happen to have a lot of upper level divergence occurring. And we talked about the upper level divergence in the forces in wind lecture. We will focus a little bit more on that when we talk about mid-latitude cyclones coming up in another unit. But what you'll basically see is, we always have warmer heights or warmer colors near the tropical regions. That's because the air is expanded a little bit. Colder temperatures mean colder heights near the north and south poles. And in the middle, we have these very close together lines. You can see the height gradient is much faster, where we have colder colors together, and that's where the wind speeds are going to be the fastest. So wherever we have these setups of the very tight gradients, like up in here, where we have lots of changes in colors over a short distance, we probably have something known as a jet stream. Okay. Jet streams form where we have very sharp temperature gradients or changes between warm and cold air, and these typically happen at about 60 north and 60 south. All right, basically where we have the intersection between the polar and the feral cells. Jet streams form at about 40,000 feet, somewhere in there. They occur at the tropopause, so they're right at the top of the troposphere. And they are basically a very narrow ribbon of very fast wind speeds. So you might have seen forecasts like this from the Weather Channel. There's a picture, a depiction of where the jet stream is located. And you can see that it's depicted by a very narrow ribbon of arrows. And this is basically where the very fast wind speeds are located, that are sort of the demarcation line, if you will, between the feral cell and the polar cell. That's all it really is. Okay? So the strong winds will concentrate into these very narrow bands at the tropopause. These are known as jet streams. Here's a map of isotachs. This is from an example of 2005. Where we had some strong jet streams going on. This is an animation, so you can kind of see how the jet streams move. The isotachs here range from these dark purples, which are slow wind speeds, to the oranges and yellows, which are very fast wind speeds. And so you can see on this map, the faster wind speeds, you can almost pick out exactly where the jet stream is located in this image. It's coming down at the beginning of the animation here. Let's let it re-loop. It's coming down from British Columbia, sort of making this U shape across the northern portion of the United States. Then it sort of reinvigorates and digs or deepens into the eastern United States. But generally you can see to the north of the jet stream we have lots of purples. Those are very slow winds. To the south of the jet stream we also have lots of purples and blues, which are slow winds. In the middle we have the battleground, if you will, between the cold air to the north and the warm air to the south. That battleground is the very sharp change in temperature, which is known as the polar jet stream. The jet stream was first found in World War II by high-flying military aircraft doing exercises between Japan and Hawaii, and several planes were taking much longer to get to Japan than others. They were actually flying against the westerly jet stream. They didn't really know it until they started launching weather balloons, and they found these very isolated, narrow areas of very fast wind speed at about 40,000 feet, and what they ended up calling this was the jet stream. Because if you are an aircraft and you can get into the jet stream, it can obviously be very beneficial to you if you want to get somewhere faster. Otherwise, it can be kind of detrimental if you're sort of flying against the jet stream. The jet streams can average about 110 miles per hour, so they're very fast-moving winds at these upper levels, found between 6 and 9 miles off the surface or right at about the tropopause. And we see 2 important jet streams in each hemisphere for a total of 4 jet streams in the Earth climate system. We have 2 polar front jets and 2 subtropical jet streams, which I show right here in this image in the upper right. The subtropical jet stream is found at about 30 north and 30 south. We have a polar jet stream that's found at about 60 north and 60 south. That is not a coincidence. It is right over the top of the intersections of the cells. So between the Hadley and the Feral, if you look right above 30 north, we probably have a subtropical jet there. If you look between the Feral and the polar cells at 60 north and 60 south, we also have a jet stream located there. So the tropopause actually changes altitude as you go from the north and south poles to the equator. We know that the atmosphere is a little bit thicker where the air is warmer near the equator, so the tropopause is a little bit higher. It slopes down, it creates this pressure gradient for us, and you can imagine higher heights towards lower heights. So there's your pressure gradient force is directed to the north. It's deflected to the right in the northern hemisphere. We get a vector that's into the page, creating westerly winds. So both the jet streams blow in a westerly fashion. If you did the same thing for the southern hemisphere, it would be deflected to the left, and you'd also get westerly winds in the upper levels due to this differences in height. Okay. So we have 2 jet streams. Again, they're located at 30 north, 60 north, and 30 south, 60 south. So we have 4 jet streams total in the Earth's climate system. Some really cool things can happen when the jet streams actually begin to overlap or couple. There's some pretty cool things here in the characteristics of jets. They wander into broad loops, which we call Rossby waves. They sweep north and south sometimes. You get into these meridional patterns. Sometimes they're more flat, left to right, west to east, moving winds across the country. Those are more zonal jet streams. They do pretty much whatever they want. They're very dynamic, very hard to predict. Sometimes the polar and subtropical jet streams merge, and when that happens, we can get very intense snowstorms or very intense severe weather outbreaks, tornado outbreaks. In fact, I can show you an example here. This is an example from May 5th, 2003. This is the afternoon of May 5th. Actually, it's the afternoon of May 4th, but it's irregardless for this example. We have ice attacks plotted on this particular chart. So the ice attacks here are shown in kind of this gray color. We can see a strong portion of the polar jet stream. So the polar jet stream doesn't necessarily have to be continuous at 60 north. Sometimes it breaks off into these pieces. Here's kind of a nice piece, though, of the polar jet stream. You can see it sort of continuous here. It actually is dipping down into the south central plains and into the southeastern United States. We also have a branch of the subtropical jet that sort of does this, and you can see this branch of the subtropical jet merging with the branch of the polar jet, and right underneath where that happened on the afternoon of May 4th and 5th, we got a very large severe weather outbreak in Oklahoma, Texas, and Arkansas, right under in Missouri, right underneath where these jet streams were merging. So you can see the two arrows there merging over this area, and that caused a very big severe weather outbreak. After everything was totaled on May 5th and 6th, we did some damage surveys here. We had 63 tornadoes, 175 wind reports, 295 reports of hail greater than 3/4 of an inch. And so you can see when those two jet streams merged, they provided a lot of upper level divergence, which caused very strong surface convergence, a very strong low pressure system at the surface, which ended up creating this very large outbreak of severe weather on the afternoon of May 4th, 5th, and then into the 6th even. So these jet streams can play a large role in extreme weather events as well. All right, so to this point, we've reviewed the 3-cell model, which is basically the single cell model, allowing the single cell model to rotate. The rotation of the Earth breaks it down into 3 cells. We talked about the 3 cells, the Hadley, Ferrel, and the polar. We defined the intertropical convergence zone, which was the basically the demarcation line between the Hadley cells. We talked about the doldrums, the horse latitudes. We talked about how surface winds are not a great example of what's going on in the upper levels because of these differences in height, and I just introduced you to the polar and subtropical jet streams. So hopefully all of those things come test time are sort of able things that you can go over and review. The jet stream is really nice because in a weather forecast, if you're north of the polar jet stream, you're probably being influenced by a cold air mass. If you're south of the jet stream, you're probably being influenced by a warm air mass. And it really is that easy sometimes. If you're in a stormy pattern, you're probably right underneath the jet stream. So if we get these very large cold air outbreaks in winter, it's just that the jet stream has dipped south of Chicago. If we get into very hot patterns, it's probably because the jet stream is to our north. If the jet stream is right over us, it's probably going to be a lot of snow or a lot of precipitation in the summertime, maybe lots of storms. Because it's very active, we have low pressure systems that are traversing through the jet stream. If you're not underneath the jet stream, it's probably slow wind and you're being influenced by either a cold air mass or a warm air mass. So the jet stream has huge implications on sensible weather conditions at the surface, not only temperature, but precipitation as well. Let's take a look at how the jet stream relates to surface pressure and what's going on. If we have an upper level Rossby wave and we see a trough, we said we have convergence, right? The parcels that are coming into the toll booth and then they speed up and we have upper level divergence. We mentioned in Unit 11 that upper level divergence corresponds to surface convergence. The air rises and basically diverges aloft. When it converges aloft, it sinks and then diverges at the surface. So underneath or just east of this upper level trough axis, just to the right, we have areas of great upper level divergence that corresponds to rising air and surface convergence. So when we see these upper level Rossby waves, we always look just a little bit upstream for the development of low pressure systems. And we're going to talk about these other features, the cold fronts that form, the warm fronts that form when we get to fronts and air masses. And we're going to see that this really, at the surface here, dictates whether or not it's going to be warm out, it's going to be raining, if we're going to have cold weather, warm weather, disturbed weather, maybe clear skies and high pressure, which is exactly what we're experiencing today on when I'm recording this lecture. We are underneath the influence of clear skies, high pressure. There are literally no clouds in the sky today. We are underneath the influence of a broad area of high pressure because of upper level convergence that is passing over our area. I'm going to skip this just to say that precipitation is very zonally distributed in terms of the surface of the Earth. You can see that these broad areas of 30 north and 30 south are the world's largest deserts. The Argentinian downsloped areas, South Africa, Australia, the Saharan Desert, the Gobi Desert, the desert southwest United States. All of these areas are basically under the influence of subtropical sinking air for the most part. And some of the world's largest deserts, which you can't see in this image, are actually the North and South Pole. The North and South Pole see sinking air from the very dense cold air that's sinking on top of it. And so we see very dry climates wherever we see these large anticyclones or these large areas of sinking air. So the rising air, like the ITCZ, creates these very nice, lots of precipitation, over 80 inches of precipitation here in Central Africa, in central portions of South America, and Indonesia, where we get lots of precipitation due to the ITCZ and the fact that there is low pressure and rising air most of the time. Most of the controls on precipitation, again, are just these broad subtropical areas of high pressure and the broad areas of cyclonic activity or low pressure systems. Couple that with the topography that we talked about, the rain shadow effect of parcels going up and over mountains, and you can basically determine or govern where areas are going to achieve or receive a lot of precipitation versus those that are not. Now, last slide for today. I talked about the subtropical and polar jet streams. I did not want to end this lecture without talking about the final jet stream that you might hear about someday. That is the low-level jet stream. This is not in the tropopause area. This is actually found just a couple thousand feet off the surface of the Earth, between 850 and 900 millibars. This is actually a very strong jet stream that occurs typically at night. Okay? At night, the surface of the air becomes stable. It sort of decouples with the surface of the Earth, and we get very fast winds in the summertime that create this low-level jet stream. And it is basically vital to the precipitation in the Corn Belt in the central Midwest. If you've ever been woken up at about 3 or 4 o'clock in the morning by a very large thunderstorm complex, it's probably something called a mesoscale convective system that's forming on the nose of one of these low-level jets. And we're going to talk about mesoscale convective systems when we get to severe weather, and we're going to see that they are very prolific lightning, precipitation, and damaging wind producers, and they often occur in June, July, and August in the central portion of the United States. So we'll talk about the low-level jet a little bit more. I just wanted to introduce it to you now that there is another jet stream. The interesting thing about the low-level jet is that it does not flow west to east. It actually flows from the south to the north. So it is a southerly jet stream that transports moisture from the Gulf of Mexico northward into the north central plains, places like North Dakota, South Dakota, Iowa, Missouri, and into Illinois. So the low-level jet stream is a very interesting phenomena. It aids in the development and sustenance of summertime thunderstorms, and we're going to see that it plays a vital role in providing the moisture needed to produce thunderstorm activity in the summertime in the plains, and it brings a lot of precipitation to the agriculture-heavy portions of the United States. So it's a very important feature that we do see at night sometimes in the central plains, and we'll talk a little bit more about that when we get to severe weather. So that's it for global circulation. Hopefully you have a better appreciation of exactly why the winds blow the way they do in different portions of the Earth system. And we see, again, generally westerly wind flow in the mid-latitudes and easterly wind flow in the tropical and polar regions of Earth's climate.